Okay, our last topic for this chapter and unit is called deBroglie wavelengths. And deBroglie was a guy that sort of threw something out there and it ended up being true. His logic was, well, if we said that anything that was a wave can be thought of as a particle, right? So anything that was a light or whatever that we knew that was waves, but now can act like a particle due to Einstein and Planck and photoelectric effect and Compton effect and all that. deBroglie said, well, is the reverse true? Things that we know that are actually particles, are they actually traveling as a wave? And he published that, and nobody really took him serious. But Einstein read it and kind of agreed with his ideas. He's saying basically if it works one way, it should work the other way. So what deBroglie did was he combined our momentum of a particle with momentum of a photon, put those two together, and he said, well, we can actually calculate the wavelength of a particle by going h over mv. So what it does is it gives us the ability to calculate the wavelength of any kind of particle that's moving. So let's do our first example. Let's actually figure out what the deBroglie wavelength is of a baseball. So if you throw a baseball, what that means is we have a particle that's moving. It's got mass, it's got velocity, but we can actually calculate the wavelength. So if we plug these numbers in, we go our 6.63 to the negative 34, divide that by the mass of the baseball, so 0.2, times its velocity is 15. If we actually do that calculation, we get a wavelength of 2.2 times 10 to the negative 34 meters. So even though, according to this, our baseball is actually traveling as a wave as we're throwing it, but the wavelength is so tiny, 2.2 to the negative 34, we'd never be able to see it. It's going to look like it's just traveling in a straight line. So that was deBroglie's theory. Einstein agreed with it, but the hard part was to prove it. So remember with the diffraction, we basically had to get a diffraction grating small enough that would match the wavelength of light, and then we could actually see the interference patterns. So in sort of the same sort of thing, we would have to get a diffraction pattern to the negative 34. Well, that's too hard to create, so that's not going to work. So what deBroglie came up with the idea saying, well, what happens if we use a smaller particle? We know an electron's a particle, so let's actually try to figure out the wavelength of an electron that's moving. So if we go for this question, we've got 100 volts. So first thing we're going to have to do is figure out what the velocity is going to be when it goes through a potential difference. So here's a good review question. So remember we have 100 volts, our electron is going to move across the plate. So what we did was we said our energy equals QV, and we know energy of the electron then is going to be converted to 1/2 mv squared. So our first step is figure out our energy to be 1.6 to the negative 19 times it by 100 volts. So that gives us 1.6 to the negative 17. And then we want to take that energy to go 1/2 mv squared. So we plug that in, solve it for velocity. I won't bother doing this step. You can do that on your own. Just put that energy divided by 1/2 times its mass of an electron, and we get a velocity of 5.93 to the 10 to the 6. So now that we have that, we can basically calculate our wavelengths. I'll just do it down below here. So our wavelength would be h over mv. So we just go h divided by the mass of the electron times the velocity of the electron, and we end up getting a wavelength of 1.23 to the negative 10. So still very small, but these are actually somewhat doable. So there's a couple of guys that said, well, they just by doing some measurements, so the size of a crystal, so like a kind of a clear metal, ends up having gaps of about that size. So what they did was they would basically shoot electrons through this crystal, and they actually saw a diffraction pattern. So by getting a diffraction pattern, then we knew that these particles, these electrons that are being shot, had to be just like going through a diffraction grating, and we end up getting a pattern that you see in this picture. It ends up giving us just like a Poisson spot or just like wave interference. So what these guys proved and what deBroglie predicted end up being exactly the same. So indeed deBroglie was right, basically saying that anything that's a particle that's traveling is actually going to be traveling in a wave pattern. So this is sort of the final tie to these two topics, that all things that are waves are actually particles that are traveling in the wave, and all things that are particles are actually traveling in a wave pattern instead of in a straight line. And that's it for this unit and topic.